Okay. So, okay. So today I'd like to start talking about what's called the boundary at infinity of a cat minus one space. So first, let's look at a simple example which we all know, which is the n-dimensional hyperbolic space. Let's take the ball model. Okay. So Hn is the unit ball in Rn. So for the unit ball, its boundary in Rn is just the unit sphere. Sn minus 1. Okay. Now, we can ask, is there a way to define this boundary intrinsically in terms of the geometry of the inside, right? So for example, if I take a point on the boundary, say this point, let me call it xi, okay, then how can I understand xi in terms of the inside? Well, we know in the hyperbolic space for any point in the ball, right, there's going to be a geodesic. So if I take any x here, there will be a geodesic, a unique geodesic ray which starts from x and ends at xi, right? What will this ray be? Remember what geodesics in the ball are. They're arcs of circles which are perpendicular to the boundary, right? So here this will be an arc of circle which passes through x and xi and is perpendicular to the boundary, right? Yes?
Yes.
Okay. So do you understand why the geodesics are arcs of circles perpendicular to the boundary? Does everyone understand why is that so? Why is that so? Anyone? Why are the arcs of circles perpendicular to the boundary?
So we can look at the upper half space model.
Okay, let's look at the upper half space model. Fine. Then what do we do?
Here we already know that any vertical
Correct. Verticals are
line,
geodesic. That's correct.
verticals
Yes,
are geodesic.
correct.
Now I can, there is always a isometry between any vertical line to any circle that intersect the
Mm,
that base plane perpendicularly. That I can do.
Why is there such an isometry?
So I take 2 points on the circle
So let's take,
that intersect, and I
well,
can take
let's
that
do it this
two.
way. Let's take 2 points. And so we know there is a geodesic joining them, right? Because
Yes.
I can always move 1 point onto the vertical axis,
Hmm.
right? And then I
Right.
can,
Right.
then this, if I identify this point at height 1
Hmm.
with, I identified with the origin using my isometry here,
Hmm.
this isometry that we constructed from the upper half space to
Yes.
the ball. Then once
Yes.
I'm in the ball, then
Hmm.
my other point, right? The other point goes somewhere else.
Hmm.
Okay, so over here I get the ball, the origin, and I get some other point. Now this vertical geodesic goes to the vertical radius here, right?
Hmm.
Okay. Now I can always rotate around the origin to move this point to the vertical,
Yes.
right?
Yes.
So
Yes.
then, yeah, or the other way to see it is once I'm in the ball, I know what the geodesics through the origin are. They're straight lines, right?
Yes. Right.
Okay. Now I use the fact
Sir.
that one second, let me finish.
Okay. Okay.
So if I look at the inverse of this map T, this is actually what is called a Mobius map in n dimensions.
Hmm.
So that means it's given by a product of reflections in hyperplanes and inversions in spheres. Okay, so this belongs to what's called the Mobius group of Rn union infinity. So this is a group in n dimensions acting on the 1-point compactification of Rn, which is
Hmm.
the group generated by reflections in hyperplanes and inversions in spheres.
Perpendicular.
No, just all inversions in spheres.
Okay.
In inversions in all spheres. This is a group
Okay.
acting on all of Rn, not on Hn.
So whole of Rn. Yes. Okay.
This is a group acting on all of Rn.
Whole of.
Okay. So remember, what is the inversion in a sphere? If I take a sphere with center P, then the inversion is basically you take X and you draw the radius passing through X from the center and you extend it to a point X star such that the product of the distances Px star is equal to what?
The radius of squared of the radius.
Right, is equal to the radius squared. Okay. Is it clear? This is the inversion in a sphere of radius r. All right. So you
Yes.
see, since the inside to the outside and the outside to the inside, and it fixes every point on the sphere of radius r, right?
Hmm. Yes.
And the center goes to infinity and infinity goes to the center, right?
Yes. Right.
Okay. Now, if you take these maps together with reflections in hyperplanes, so I take all hyperplanes like this. So any Euclidean hyperplane, I have a reflection, right?
Yes.
A Euclidean reflection. So I take these reflections and I take these inversions. Okay. Then, bad picture. they generate actually a finite dimensional Lie group called the Mobius group. Okay. So the fact that this is finite dimensional is a bit surprising because see, these reflections, we know these generate the orthogonal group, right? Well, the isometry group rather. They don't need to be reflections in hyperplanes through the origin. If you take reflections in hyperplanes through the origin, those will generate the orthogonal group, right? Yes.
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 Now, if you take reflections in all hyperplanes, not necessarily passing through the origin, then you will get orthogonal transformations as well as translations, right? You'll also get translations. So you'll get the full isometry group of Rn. So those are affine linear maps. Those are affine linear maps of the form x goes to OX plus B. Okay.
Yes.
And it turns out to this group. So in 2 dimensions, these are just the affine linear maps, complex linear maps, right? Well, if O is in SON, if it's in SON, then this is lambda z plus AZ plus B, right? Where A is a non-zero complex number. Well, a complex number of modulus 1, sorry. And then, well, if you add inversions in spheres, so actually, well, so if I add scalings to this and I take inversion in the unit sphere, x over norm x squared. So this map we already saw. Then this generates the same group. Okay, that you can see. It's not very hard to see. These two are the same group. So here O belongs to O and R, lambda positive, B belongs to Rn. Okay. Now, why am I writing it like this? Because these maps, these are rotations, scalings, and translations and reflections. These send lines to lines and circles to circles, right? In Rn. Yes?
Yes.
Now, what happens to lines and circles under the inversion in the unit sphere? Well, lines through the origin go to lines through the origin, right? They go to themselves. But if I take any line which is not passing through the origin, then what happens if I take a line which is not passing through the origin? Well, this lies in a plane, right? This is part of a 2-dimensional plane.
Right.
And in that plane, my unit sphere intersect that plane is just the unit circle in that plane. And it's a plane passing through the origin. I take a plane passing through the origin, right? So that plane passing through the origin is invariant under my inversion in the unit sphere, right? Because all these lines passing through the origin go to themselves. So this plane goes to itself. So in this plane, what is inversion in the unit sphere? It's the same as just reflection in the unit circle in this sphere, right?
The line goes to circle.
So therefore, the line goes to a circle in this plane, right? Because the restriction of the inversion in the unit sphere to this 2 plane, it becomes a reflection in the unit circle. And we know that reflection in the unit circle maps lines to circles. Lines not passing through the origin go to circles. Similarly, circles, any circle in Rn is contained in a plane, right? And well, there you have to be a bit careful because that plane may not pass through the origin. That plane may not pass through the origin. So yeah, if it's a circle in a plane passing through the origin, then we're fine. Otherwise, I'll have to think about it a bit. Yeah. For a line, at least it's clear. A line, the image of a line will be a circle, right? In a plane passing through the origin. But it's true that all circles also map to circles or lines. All right. And we saw that this map, this inversion in the unit sphere, this preserves angles, right? Because it was a conformal map, right? If I call this map F, then the norm of dfx v was some function lambda of x into norm v, right? We saw this, right? We did this computation. Yes?
Yes, yes.
So this means that lengths of tangent vectors are scaled by the same amount at the point x. Therefore, the angle between tangent vectors is preserved, right?
Hmm.
Yes, because inner products get multiplied by lambda squared, basically, right? By polarization identity.
Yes.
So therefore, the angles are preserved, right? So these are, in fact, it turns out that this group is the same as the conformal group. So this is a theorem of Liouville. This is the same as the conformal group of Rn union infinity. So where conformal group means diffeomorphisms from Rn union infinity to itself. So this is a manifold, right? It's diffeomorphic to the sphere. You have charts on it which make it a manifold of a compact manifold of dimension n, which is diffeomorphic to the sphere n sphere Sn. And there you can talk about conformal transformations. So these are maps from Rn union infinity to itself, diffeomorphisms, which preserve angles. Okay. So these are angle preserving diffeomorphisms. So one direction is easy, that any Mobius map preserves angles, because these rotations, scalings, translations, these reflections all preserve angles. What you need to check is that inversion in the unit sphere preserves angles, right? No, sorry, we know that inversion in the unit sphere preserves angles. So therefore, all of these preserve angles. So the group preserves angles. The Mobius group preserves angles. What is quite non-trivial, what is Liouville's theorem is the converse. Any conformal map of Rn union infinity is a Mobius map. Okay. So this is a theorem of Liouville. Okay. So in 2 dimensions, we already know this, except you have to be a bit careful. In 2 dimensions, this Mobius group that I'm defining is a bit larger than the usual Mobius group we study in complex analysis, because this includes reflections, right? So it has orientation reversing maps. So in 2 dimensions, this would be the usual Mobius group, AZ plus B over CZ plus D, together with the reflection in the real axis or complex conjugation, Z goes to Z bar, right? So those will give you anti-holomorphic maps. Okay, so A Z bar plus B over C Z bar plus D, right? So together you take those two, and the holomorphic Mobius group is a subgroup of index 2 in the full Mobius group. All right, is that clear?
Yes.
Okay. All right, so these send lines and circles to lines and circles, these Mobius maps. And this T by construction, you can see this is a Mobius map, right? If you recall the construction, it was just translations and scalings. And at one point we had an inversion in the unit circle. So this is a Mobius map. So therefore, this straight line through the origin will go to a circle, right? In the upper half plane. So here you'll get a circle. All right. And this straight line through the origin, it meets the boundary here at right angles. And Mobius maps, they preserve angles, right? So therefore, this circle will meet the boundary here at right angles. Okay. Fine. Right?
Yes, sir. Yes.
So now you can see that any geodesic in the ball will be an arc of circle meeting the boundary at right angles, because you take any 2 points in the ball, then they correspond to 2 points in the upper half plane. The geodesic joining those two is a circle meeting the boundary of the upper half plane at right angles. So therefore, its image under this Mobius map T will be an arc of circle meeting the boundary at right angles here. Is it clear now?
Yes.
Okay. So this is just now Euclidean geometry that we're doing about these, well, Mobius maps, inversions and so on. So using this description of geodesics, it's easy to see that for any point on the boundary sphere and for any point in the inside, there's a unique geodesic ray joining X to Xi, right?
Mm-hmm.
So
Right.
exists unique. This is just a Euclidean geometry. I mean, because I mean, X and Xi are contained in a two-dimensional plane, right? In a copy of H2. And in that copy of H2, in a circle, you know that given a point here and a point here, there's going to be a unique circle like this, which is perpendicular here and here, right?
Right. Yes.
Okay.
Yes.
Okay, I mean, basically if I look at all circles which are perpendicular to the boundary here, then that will give me a one parameter family of circles like this. Right? This is the family of circles. These will be circles tangent to this radius, right? At the point, at the boundary point. I'll get this family of circles, right? Yes?
Yes. Yes.
And you can see for this family of circles, well, do they intersect the boundary at right angles? They don't, not all of them. Am I missing something? Wait, I'm missing something, I think. I think I'm missing something. Well, let me just be careful. No, these will all intersect the boundary at right angles. These will all intersect the boundary at right angles. There's a little argument which I can't make up right now, but you can see these circles through every point in the disk, there'll be exactly a unique such circle passing through it, right? In this one parameter family of circles, right? Yes, you see that? Yes, hello?
Yes. Yes, sir.
Is that okay? Yeah, you see there'll be a unique circle passing. So therefore you get this. So there exists for all Xi in boundary Bn, X in Bn, exists unique geodesic ray gamma, such that gamma 0 is X and gamma infinity is Xi, right?
Yes.
Where gamma infinity means the limit of gamma t as t tends to plus infinity. Okay. Now, so basically any boundary point, it gets identified with this collection of geodesic rays, right? For every point inside, I'm getting a geodesic ray. So abstractly, what is a boundary point? It's the same as this collection of geodesic rays, right?
Yes.
Now, how can I characterize these geodesic rays? Well, it's an easy calculation to see that if I take any two of these geodesic rays, say like this and like this, then the distance between these two geodesic rays not only does it, the hyperbolic distance, it stays bounded. Not only that, it actually goes to 0 as t tends to infinity. If you take appropriate points along these geodesic rays. What do I mean by appropriate points? Well, you have to take what's called a horosphere. So this is easy to see in the upper half plane. Let me show you in the upper half plane. So in the upper half space, so I know that, look, if I have any boundary point, I can always map it to infinity, which is in the boundary of the upper half plane, right? Okay. This is the boundary in Rn union infinity. Is that clear? Yes? Because by a rotation, I can move it to the North Pole, and then my Mobius map will send the North Pole to infinity. Is this clear? Yes?
Yes.
Yes, sir.
So now all the geodesics passing through Xi, they go to geodesics passing through infinity, right? Geodesic rays passing through infinity. Now, given any point X here, what is the geodesic ray passing through infinity? From starting from X and going to infinity, what is the geodesic ray? Come on, you should know this. This is obvious. What is it? It is a, I'm giving you a hint here.
Vertical line.
Yeah, it's just the vertical line, right? It goes to infinity, right? It ends, it goes to the point at infinity on the boundary, right? Yes. So now infinity corresponds to this collection of vertical rays, all right? Yes. Okay.
Yes, sir. Yes. Fine.
Now, what can I say about the distance between these two rays? Well, if I take 2 points which are at the same height, so first of all, X and Y may not be at the same height. So let me take a point on this geodesic through Y, which is at the same height, right? Okay, so I get a horizontal plane like this. Let's say the horizontal plane containing X. Okay, and let's say, so there's a point of this geodesic vertical through Y, which is on this horizontal plane, right? Now, let me call this hyperbolic distance, say B. Okay. So then, if I call this point, say, Y tilde, now I look at points which are at distance T from X and T from Y tilde. So these are at the same height. Okay. So this distance is T and this distance is T, right? So what is the distance between these two? Well, I don't need an exact formula for the distance. So if I call this xt and I call this yt, right? Then this distance is less than or equal to the length of this arc, right? Distance xt yt.
Sir, how did you
Is
get
less-
that y tilde?
Y tilde is the point on the vertical which is at the same height as X, right? It's in the same horizontal plane as X. There's a horizontal plane here, right? Passing through X.
Yes, yes.
So Y tilde, it's a vertical. So there'll be a point on this vertical line which passes through this horizontal plane, right?
Yes, sir. Yes.
That is my Y tilde. And then after that, from this horizontal plane, I'm going up a distance T on both X and from both X and Y, right? So
Okay.
now I get two points on these two verticals, which are at the same height, xt and yt. So I can join these by a horizontal line, right?
Yes, sir.
Yes. So
Yes.
now the distance between xt, yt is less than or equal to the length of the horizontal line, right?
Yes, sir.
from xt to yt? Okay, so now what is this height? So so xt and yt in this so xt and yt have the same height, so they're of the form some p comma ht, and yt is also q comma ht, right?
Yes.
Yes.
Yes, sir.
And what is ht? Well, I know that the distance from, so if x is equal to
Exactly.
is, suppose x is equal to p comma h0, right? Then I know that t is equal to the length of this geodesic from x to xt. So that is equal to the integral from 0 to t of dy by, well, so I mean the height is going from h0 to ht, sorry, so it should be from integral from h0 to ht, right? dy by y. Yes, this is the hyperbolic length. So this is log ht by h0, right? Yes.
Yes.
Yes, sir.
I think this is correct. Yeah.
Yes, sir.
Right. This seems correct. Yeah. So therefore, ht is right. Yeah. So ht is h naught e to the t. Okay. Fine. So what will the length of the horizontal line be? This will be the Euclidean length of this line divided by the height, right? So this is mod p minus norm p minus q divided by the height, which is ht, right? Is this clear? Yes, because what is the hyperbolic metric? It's the
Right,
Euclidean
right.
metric
Yes,
divided by
yes.
the height. The height is constant, so I'll just get the integral of the Euclidean metric, which is just the Euclidean length, right? So it's
Right.
just norm p minus q by ht. So this is norm p minus q by h naught into e to the minus t. So this tells you that actually the distance goes to 0, right? Between
Right.
xt and yt. So these two geodesics, not only are they staying in bounded distance from each other, actually the distance between them is going to 0, right? And not only is it going to 0, it's going to 0 exponentially. So 2 points which start on the same horizontal plane, right? 2 points which start on the same horizontal plane, the distance between the vertical geodesics goes to 0. Okay.
Yes.
Now if I come back to the ball, this horizontal plane, this will go to what? So planes under Mobius maps, they go to spheres. Okay. So this will go to a sphere which passes, infinity goes to xi. So this will go to a sphere in the ball passing through xi, right?
Right.
And it will be tangent to the boundary at xi.
Right.
Okay. So I'll get a sphere like this, which is tangent to the boundary at xi. And if I take any 2 points on this sphere, then the geodesics joining, the rays joining them to xi, this distance goes to 0 exponentially, right?
Yes.
And these other, at these heights, I'll get these other smaller spheres, you see? So, so the picture is like this. Basically, it's like in the disk. The horizontal planes will go to these small spheres, which are all tangent at the boundary point. So these are called horospheres based at xi. Okay. These are called horospheres based at xi. And if I take any 2 points on the same horosphere, right, and join them to xi, then the distance then under when I go along the geodesics, they'll stay in the same horosphere at each time t, and the distance will contract exponentially, right? Okay, the distance between two geodesic rays perpendicular to the same horosphere. These are the perpendiculars to the horosphere.